Welcome to Physics 456, Statistical Mechanics. We're about to begin today on what I think is a very exciting course, and it will cover quite a number of topics in this fundamental discipline in physics. Applications range from condensed matter physics, particle physics, and all kinds of other things. And so with that, let's sort of set a kind of a background for where we want to go. So we can think about Newtonian mechanics and the way we explain classical mechanics with this deterministic system. For those who took modern physics, you recognized in that course that there were two conditions where Newtonian mechanics wasn't enough. And the first was for particles that travel too fast. We needed to incorporate Einstein's special theory of relativity to account for the motion of those particles. And then we found that for particles that were too small, we had to incorporate quantum theory, quantum mechanics. And those were two important revolutions in the early 20th century. But there's another aspect that you may not have thought about, and that is, suppose you have too many particles. So for example, let's take a mole of an ideal gas. That's 6.02 times 10 to the 23rd particles. If you were to try to analyze the motion of all of those particles, even the biggest, most powerful supercomputer would fail. And so that's a problem. And oftentimes, not only that, we have a system where we don't have complete information about all of the entries in the system. And that's the perfect time to invoke statistical mechanics. It has wide application. It will provide the correct answers. And I think what you're going to find as we go through the course is it's really elegant and beautiful in the way it analyzes physical systems. So for starters, we're going to discuss probability. Probability in statistics to analyze microscopic systems. As you might imagine, most real systems that you're going to analyze in the physical world are going to be very large. And so we have to have a way of compensating for the fact that we have way too many particles to just use Newton's laws with. Now, from a historical perspective, the first real use of statistical mechanics was in explaining topics in heat and thermodynamics. The early pioneers in statistical mechanics, Boltzmann and Gibbs, both made amazing discoveries in this world, worrying about problems in thermodynamics. Thermodynamics, in and of itself, is a very fulfilling field, but as you'll see as we go along, it lacks certain things. So, for example, it describes macroscopic phenomena very well. The laws of thermodynamics were discovered empirically, but as you'll see in statistical mechanics, we're going to be able to arrive at all of the laws of thermodynamics from first principles in statistics. In thermodynamics, you also had no need to believe in atoms, but in statistical mechanics, we take advantage of the very small to explain the very large. We use statistical mechanics to use a microscopic point of view to predict macroscopic behavior. So where do we start? Well, in the way we want to start, we're going to use the rules and postulates of quantum mechanics. Now, that doesn't mean that you have to know quantum mechanics thoroughly to understand the way statistical mechanics works. In fact, a lot of the systems that we use will end up being classical in nature. And oftentimes the classical statistical mechanics will suffice. But we will, in this course, study quantum statistical mechanics and some of the great features of that area. Next thing we're always going to assume is that the system that we study will always be in equilibrium. So we're going to be studying equilibrium statistical mechanics. You can, and people do study non-equilibrium statistical mechanics, but those problems are much, much, much harder. It is a very, very difficult discipline, and as you'll see, there's plenty involved in just understanding systems in equilibrium states. So here's the strategy we're going to take. Suppose we have a great number of systems. We may not be able to predict the outcome of a particular system in a particular experiment, but if we envision an ensemble of systems, maybe a great many systems, all configured in the same way, we can think about how many of those systems would have an outcome that we desire. So let's take a really simple example, a non-physics example. Let's say, let's talk about throwing a die. Okay, if I throw a die, the probability of obtaining an ace, or 1, is 1/6. And I would expect if I had an ensemble of 1,200 dice, and I threw all 1,200 of them at once, I would expect to get something like 200 aces. And the larger the sample size you take, the closer you're going to get to hitting on those probabilities exactly. So one of the things that we do in physics is to think about very large ensembles. Taking it a step further, we can look at this, even this very simple dice experiment, in a couple of ways. One, we can think of a large number of pairs of dice, let's say. Suppose we want to throw, look at the outcomes of throwing 2 dice. Suppose we took, 1,000 pair of dice and threw them. We could make some predictions throwing all 1,000 pair. Or I could take just 1 pair of dice and throw it 1,000 times, and the answers should be roughly the same. And so what we would say if we asked ourselves, what's the probability of obtaining a double ace? Well, that would just be the fraction of times I could obtain a double ace out of the total number of possibilities when I throw 2 dice. So we can actually do this experiment, but our goal in statistical mechanics is to predict what results will occur. Now, as in any and all sciences, you are held hostage to experimental results. It's all well and good to come up with a great theory, but eventually your theory has to be confirmed by experiment. And of course, we're not going to be running experiments in this class, but suffice it to say that one of the reasons we study statistical mechanics is to show that, make predictions in all kinds of systems, and discuss the fact that when the experiments are carried out, the answers turn out to be correct. One of the beauties of statistical mechanics. Let's do, as a way of sort of broaching the probability aspect of the course, let's start with a problem that we call the random walk problem. And we'll do the problem like so. Suppose we have a college student who has had a bit too much to drink and is standing outside a bar under a light post. Here's my light post. And let us say that he's taken in so much that he really can't distinguish a left step from a right step. And the probability of him taking a left step is exactly equal to the probability of him taking a right step in front of that lamppost. Let's say that every step he takes, whether it's to the left or to the right, has some length L. Okay? Let's call the probability of him making a step to the right, let's call that P, and let's call the probability of him making a step to the left, we'll call that Q. And of course, he's going to make a step either way, so the sum of the probabilities, of course, has to equal 1. If the ground that he's on is perfectly straight, it's a pretty good assumption to say that P is equal to 1/2 and Q is equal to 1/2. In other words, the probability of him taking a left step is just the same as the probability of him taking a right step because he's moving so randomly. But of course, that doesn't have to be the case. Suppose we had an incline one way or the other. That could cause the student to step more in one direction than the other. But for now, let's just assume a nice straight level, a level street that he's standing on. So the question I'm going to ask is, if the student has taken n steps, n being a large number, what is the probability that his displacement will be equal to x, m times L, where m can be either positive, negative, or 0. What we would do then is to create some ensemble of n such students, capital N, that many students, all starting from similar lampposts with the same probability. Let's say for simplicity, let's make each left and right step be equally probable. And we ask ourselves, what fraction will be located at x equals ml after he's taken n steps? Okay? Okay, so let's say that the student takes n1 steps to the right, and then he takes n2 steps to the left. So that the total number of steps he takes is capital N, but he's taken n1 steps to the right and n1 steps to the left. Furthermore, of course, m then would just be the difference, right minus left, in his displacement. Well, let's take kind of the long-winded approach to how we might calculate this, and then we'll show you a real quick way to do it. So I could say, well, the probability of taking n1 steps is, maybe I'm going to take n1 and probability, 1/2, n1 times, and then I'm going to take n2 steps to the left, however that turns out to be. Well, I can write that as p to the n1, q to the n2, however many times he goes to the left versus the right. Okay, now we have a choice. We have n total steps, and let's create this sort of configuration of slots. I could put n items in the first slot. I could put n minus 1 items in the second slot because he's already taken a step. If he takes a third step, I can put n minus 2 items in the third slot, and so on and so forth, until I go all the way down to the nth step he takes, and that's just, I only have 1 item left for the nth slot. What this is saying that if I could tell one left step from another left step, I would say that the steps were distinguishable, and I would say that I would have this many choices or n factorial ways that he could have this configuration. But it's not quite that simple, because I can't tell one left step from the other or one right step from the other. They're indistinguishable. So that gives me an overcounting of the total number of possibilities. And the way I account for that is to divide by n1 factorial and n2 factorial. This tells me that all left steps are the same, all right steps are the same, so the total number of possibilities I have is the total number of steps he takes divided by n1 factorial divided by n2 factorial. Thus, the probability of him taking, let's say, n1 steps to the right is going to be equal to the total number of ways I can configure this times the probability of taking n1 steps times the probability of taking n minus n1 steps to the left. Okay? You might recognize this function from math classes or other places. This is what we call a binomial distribution. And in fact, I might think of it this way. I can write P plus Q to the n as the sum from n equals 0 to capital n factorial, little n factorial, n minus n factorial, p to the n, q to the n minus n. Using the previous relationships, we can say that n1 then would be equal to 1/2 of n plus little m, like displacement, n2 equals 1/2 of capital N minus little m. And so the probability in terms of m, what my final displacement is, I could write as n factorial over n plus m over 2 factorial times n minus m over 2 factorial p to the n plus m over 2 q to the n minus m over 2. So this is the probability that the net displacement x will be equal to m times L. To simplify it even further, if P and Q are both equal to 1/2, this becomes very simple. It's n factorial over n plus m over 2 factorial, n minus m over 2 factorial 1/2 to the n. And you might say, what has this got to do with physics? This notion of inebriated students at lampposts seems to be pretty far removed from serious physics. However, this represents a very common problem in statistical mechanics. It's called the two-state problem. And it happens in many, many ways. Anytime you have a system that can be in two configurations, you can analyze it in the same way as you would the random walk problem or throwing a dice problem or whatever the case may be, or I should say flipping a coin, because there are two possibilities. Let's move to a physics example. Let's talk about magnetism. So a good example of a two-state system, and we will talk about this topic many, many times during the course of the class. An atom can have spin up or spin down. So we call it spin minus 1/2 or spin positive 1/2. And so in this case, we talk about it having associated with it a magnetic moment mu, which is equal to 1/2. And it can be either spin up, which is plus 1/2, or spin down, which is minus 1/2. If both directions are likely, we might ask, what is the total magnetization of n atoms, where my total magnetization is equal to the number of atoms I have times the net magnetic moment, mu. This is a problem, as I say, we'll be studying as we go deeper into the course. Let's do a couple of examples with the binomial distribution. Some really simple examples. Suppose I have a game where I throw 5 true dice, and I want to find the probability of rolling a 6. We'll do it for several cases. One. Suppose I want to find the probability of rolling a 6 only once. Okay? Well, probability I can write as n factorial n minus n factorial p to the n q to the n minus n. If capital N is the total number of throws, little n is, in this case, the number that little n is the number of ones that I throw. P is going to be probability of throwing a 1, which is 1/6. Q is the probability of not throwing a 1, which is 5/6. And so if I want to find the probability that I throw a 1, it's going to be equal to 5 true dice divided by 1 factorial, 4 factorial, n minus n is 4, and it's going to be 1/6 to the first power times 5/6 to the 4th power. So I only have, because I have 1 success and 4 failures, so to speak. That being the case, multiply all this out, and I'm going to find that the probability of one of these rolling a 1 on one of the die is 0.4. What's the probability that I'm going to throw at least 1 ace? Now, there are a couple ways to do this. One way would be to say, well, what's the probability of throwing 1? What's the probability of throwing 2? Probability of throwing 3? All the way up to the probability of throwing 5. That's a lot of work. It's easier to do this. We know that the total probability has to equal 1. Therefore, if we calculate the number of what the probability is of throwing 0 aces, and subtract that from 1, we'll get the probability that we're going to throw at least 1 ace. So let's calculate the probability that I'm going to throw 0 aces. So I have, in this case, n is, I still have 5 dice. I'm going to have 0 factorial, because I'm going to have 0 aces. This is going to give me 5 factorial, because capital N minus little n is just 5. 1/6 to the 0, 5/6 to the 5th power. Notice 0 factorial is 1, 5 factorial cancels with 5 factorial, 1/6 to the 0 power is 1, therefore the answer is going to be 5/6 to the 5th power, or that will be 0.4. And so the probability of at least one ace will be equal to 1 minus 0.4, or 0.6. Okay, so it's a nice use of the binomial expression to calculate a probability of throwing dice.
And that was the first part of this lesson. We will continue with the second part in just a moment.